All right, this is chapter 12 review for the final exam. Chapter 12 is on probability, so we'll see how this goes. We started out with just counting theory. We had to talk, this is how many are in A, this is how many are in B, this is how many are in A intersect B. That word right there, or that symbol right there, means intersection, which means are in both of them. So we set up Venn diagrams. This is a flyby of this. First circle A, circle B. We talked about that you should start with the most specific. So the intersection of A and B is 10. And then if we come to B and there's 20 in B, well, there's 10 already in B. So 10 more would give me a total of 20. And if there's 15 in A, we already have 10 in A, so we only need a total of 5 more. So there's a Venn diagram of the situation. The question asks for A union B. Union means in A or B. Well, A or B, there's 5 exclusively in A, there's 10 exclusively in B, and there's 10 in the intersection. So there's a grand total of 25 people that are in A or B. So the correct answer there was 25. Just be aware of Venn diagrams. If the question asks for right now, how many are in B? How many are in B? This is a question that we messed up on the test for this section. A lot of you said, oh, there's 10 people exclusively in B. But this is not saying exclusively. This is just saying how many are in B. And right now there's a total of 20 in B if I look at this Venn diagram. Or in the same fashion, how many are in A? There'd be a total of 15 in A, not 5. So be very, very careful of that. Number 2 is very hard to read and has a massive thing. So we'll come back to that one if we have time, or do that one in class if I show that. Number 3, how many are in A and B or C? So they first have to be in A and B. The ones that are in A and B are in this little football region right in there. So all of those work no matter what. So I have those 8 people, or they could be in C. Well, how many are in C? We have 15, 2, 2, and then this 5 right in here, but that 5 right in there we already counted, so we won't count that again. So we have the 8 of them are in A and B, and then how many are in C would be a total of 19, not including the 5 that was already in that football. And then we add those up for a grand total of 27 would be the correct answer there. If you need more help on those types of problems, you can go back and look at the chapter 12 stuff. We also had, the complement. How many are not in A? If this was the question right here, this would be how many are not in A, or the number of them that are not in A. Well, A is this circle right here. So not in A would be everybody that's not in that pink circle right now. So it'd be 10, the 2, the 15, and these 4 that are right here on the outside, they're in the universal set. So if we added all those up, we get 14, 29 plus 2 is 31. Would be how many are in not, the number that are not in A. If you remember that line on the top, it's called the complement, and it means not. All right, then we start going to counting theory. These are totally independent events. To count these would be 8 Dows, 15 stocks, and 4 global stocks, because we're going to be millionaires someday. How many different portfolios are possible if we have to select one from each one? This is independent. We put lines out. Do you remember lines? We have 8 Dow stocks, so we have 15 NASDAQ stocks and 4 global stocks. To find out how many different ways we could purchase these, we multiply those to get our answer. Okay, so that's pretty basic. That's independent multiplication. Number 6, how many 2-letter codes can be formed if repeat letters are not allowed? I love using lines for counting. We have 2-letter codes. Repeat letters are not allowed. This is a new shocking revolution to you, but we have 26 letters on our alphabet. So the first one is 26 choices. If repeats are not allowed, then there's only 25 left over to go there. And again, you multiply these. This is very, very easy. All right, number 6, in how many ways can a committee, that should jump off the page at you, the word committee, if you remember this. This automatically means that we're going to have a combination. A combination means order does not matter. It does not matter what order we put these in. If it's a combination, we can always use the combination formula. So if you go back and look at your calculators, or go back and look at the notes from this section, it's the number of combinations from, and the first number you put down is how many you have to choose from, which in this case is 7. So the number of combinations from 7 students, and how many am I trying to pick? I'm trying to pick 4 of them. So you can go figure out on your calculator how to do the number of combinations from 7, choose 4. That should be in the probability section. It might be NCR on your calculator, 7, 4. Some calculators you put the 7, then you put the NCR, and then you put the 4. But the key to this is a committee, or another thing that means combination, is a group of people where it doesn't matter what order they're in. If it matters what order they're in, it's called a permutation, which I believe is the next problem we're going to look at. So one of the key things from this unit is knowing the difference between a permutation and a combination. This one is a permutation. Why is this one a permutation? Because it talks about batting orders. It matters what order you're in. So permutations, we wrote down a lot of key words. If you go back and look at your notes, if you're going to line things up, if you're going to arrange things, if you're going to fill specific spots, like a president, a vice president, and a secretary. That was supposed to be a P right there. That's really bad. President, vice president, secretary, or horses are finishing first, second, and third. Those are actual places to be filled where order does make a difference. That would make it a permutation. If it's a permutation, you can use lines if you want. I'll show them both real quick, but you can do the number of permutations on your calculator from, and we have 12 players to choose from, and we're trying to line up 9 of them. So you could do that on your calculator. Or permutations, you can actually just use lines if you want. You have 1, 2, 3, 4, 5, 6, 7, 8, 9 spots to fill. For the batting order, 12 people could go in the first spot because we had 12 people to choose from. But then as soon as somebody went there, there's 11 left, and then 10, and then 9, and then 8, and then 7, and then 6, and then 5, and then 4. And if you multiply all those together, you get the same answer you got here. You can test that out on your own. Remember, anytime you need to pause this video because I'm flying, you can pause and try things on your calculator and come back. How many different ways can the letters from Mississippi be arranged? Arranging letters. First of all, order makes a difference, so we can do permutations. But I just like putting lines up for this one. If we're just arranging the letters in Mississippi, how many letters are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11 lines, which would just be 11 times 10 times 9, which is also 11 factorial. If you remember the 11 factorial thing, that's 11 times 10 times 9 times 8, etc., all the way down to 1. So 11 factorial means 11 lines, 11 all the way down to 1. But for these problems, and this is a classic problem, arranging letters. It's the number of letters factorial. But if there's repeats in the set, you then have to divide by the repeats factorial because it doesn't matter what order the S's are in, or the P's are in, or the I's are in. So if we count all the I's, it looks like there's 4 I's, so I'll divide by 4 factorial for the I's. There are 4 S's, so I'll divide by another 4 factorial for the S's. And there are 2 P's, so I'll divide by another 2 factorial for those to get my grand total for that one right there. And I don't even know what that is. You can do that calculation. Check that on your calculators. All right, this is the first one that's probability. There are 12 red and 5 blue marbles in a bag. What is the probability to point out 4 red and 2 blue marbles? It does not matter what order. If we look at this, what order we get these things in. We're just trying to get 4 red and 2 blue marbles out, so it's a number of combinations. The bottom for probability is how many total choices there are. So it's a number of combinations for how many total marbles are there, which is 17 marbles. There's 12 red and 5 blue, so there's 17 marbles, and I want to pull out 4 and 2, so I want to pull out 6 of them. So that is the total possibilities. Remember, probability, as basic as it gets, is total possibilities goes on the bottom. So that's the total number of ways I can pull out 6 marbles. But on the top are the winners, so probabilities. The number of ways I could win should go on the top. Well, there's 2 separate events going on. I need to get 4 red, and the word "and" in probability means multiply, and I need to get 2 blue. But it doesn't matter what order again, so it's the number of combinations from how many red ones are in there. There's 12 red marbles in the bag, and I am trying to get 4 of them. And then if I go to the blue, it's a number of combinations from, there are 5 blue marbles in the bag, and I want 2 of them. And the word "and" in probability means multiply. So if you do that calculation with your calculator, you'll get the answer. But that idea of it does not matter what order they come out in. And that's a probability problem. Number 10. A license plate consists of 2 letters, including O and I, followed by a 4-digit number that cannot have a 0 in the lead position. How many plates are possible? So we need 2 letters, followed by 4 digits. The 2 letters, excluding O and I, that was the bell, so I'm going to stop this because children are going to run in here. So I'll finish this up when I can. Maybe I won't.